This problem states, for the element shown on the surface of the circular beam or shaft fixed to a wall with radius c, axial force P, and torque Tap, what is the larger of the two in-plane principal stresses? So to start this problem, let's take a look at an element that might be on the surface of this circular beam or shaft. And let's draw the state of stress. We see that there's this force P acting on the end of the beam, kind of like a bar, and that will probably contribute to a sigma x. It will contribute to a sigma x in this direction if x is this direction. And then we also see that there is some shear stress that's going to be induced by Tap. And we've talked about this before. One way to think about what's happening with an applied torque that's twisting a shaft is to look at the deformation or think of the deformation. And this Tap is going to be acting in this direction, and it would essentially be deforming the element like this, so that this element will end up being a little bit higher up. If you were to think of an orthogonal direction to x, we'll call it y, and this right side would be a little bit lower, and so that would be corresponding to this downward arrow here. And the state of stress, if we did not have P on the system, from only Tap would be essentially one of pure shear. So you see the pure shear elements that we have right there. So let's redraw the element with a square out here in space somewhere, but it's associated, of course, with this point on this surface of the circular beam or shaft or bar. And we see that we have an x coming out the left side. Why is that? Because there's an x coming this direction. I'm going to think about positive x coming out here. And then I'm going to think about a y in this direction. Now, this is a little bit maybe tricky because this would then mean that z is going into the board. But let's just go ahead and leave it as is right now. They're not asking us about the angle. They're not asking us about sigma z, which, well, would be 0 here. And we're not asking for the state of maximum shear stress, max in-plane shear stress. So let's just go ahead and draw y as going up there, keeping in mind that x cross y will be into the board. We have sigma x that is in line with the x as we've drawn it here. We then also have the shear stress right on this left side, and so that would be a tau xy, and we see that this is on the x face and it's in the positive y direction. And we've also talked about this in the past, but we can once you know one of the shear stresses on a box, 2D box or square, you can draw the rest. So it might be a good idea to say, okay, these stresses are going to meet in this corner, and then we have the other stresses, all with magnitude tau xy, and all really tau xy's that keep this element in equilibrium. Sigma x is equal to this p, this force p divided by the cross-sectional area, which is pi c squared. So we have sigma x equals p over pi c squared. Tau xy is going to be the Tap, okay, like that, and it's TC and J, all right, or well, that's what we say in New Jersey, or that's what I say in New Jersey, TC over J, okay, so Tap times C, which is the radius, all over the J, which is going to be pi over 2 C to the fourth. This simplifies to 2 Tap over pi C cubed. And in this section of the session, we had derived the way to calculate out what the principal stresses are. And so sigma 1 or sigma 2 can be given as the average of the given stresses plus or minus the square root of this quantity. And so the shear stress comes into this part. Well, we have a sigma x, Do we have a sigma y? We don't have a sigma y. So sigma y is equal to 0, and tau xy is given by this equation here. So if we're interested in the maximum in-plane principal stress, we can say that sigma x is going to be positive the way we've drawn it. And so we have positive here. So we're going to, and this quantity has to be positive because it's, well, we're taking the square root of something. And so it's going to be this average plus this. So the maximum in plane principal stress is just going to be sigma x over 2, sigma y is equal to 0, plus this quantity here where, again, sigma y is equal to 0. I hope you find this example helpful. Thank you.